And after the lunch break, in the afternoon session, we have another plenary talk by Dr. Sumanto Kundu from University of Padova, Italy. And also we have two oral presentation sessions, and then we shall conclude. So let me stop sharing now. And without much delay, we can start now. And just a note to all the participants to please turn off your camera to save some bandwidth, as well as keep yourselves muted. And without much delay, I shall request our Professor Muktish Acharya from Department of Physics, Presidency University, to say a few words about this conference and to take the charge of this first plenary talk. Thank you all.
Uh,
Please stay tuned.
okay, thank you, Shovik. So let me briefly introduce Sebabrata Mukherjee. Dr. Sebabrata Mukherjee is currently working as an associate professor in the Department of Physics, IISc Bangalore. He was awarded the BSc in Physics from the University of Calcutta, probably from the VC College Rahura
That is correct.
in 2010, and the MSc in Physics from the Indian Institute of Technology, Delhi in 2012. Prior to his doctoral research, he worked as a project associate at IIT Delhi, and he got his PhD from Heriot-Watt University, Edinburgh, in the area of experimental simulation of solid-state phenomena in photonic structures, and was subsequently awarded the 2016 Macfarlane Prize for the most outstanding contribution to the research at the university. He worked as a research associate at Heriot-Watt University and postdoctoral scholar at the Pennsylvania State University, USA. His research interests include photonics and condensed matter physics. And now I would like to request Dr. Mukherjee to share your screen and start presenting.
Um,
Dr. Mukherjee, please.
yeah, thank you, Professor Muktish, for the kind introduction. I think my screen is visible now. Can you see my slides?
Yes,
Yes, it is
it is coming
visible.
up.
Yes.
Okay,
Yeah,
thank
we
you.
can see.
Okay, thank you. So, first of all, I would like to thank the organizer, Presidency University, for giving me this opportunity to present our work. So, as you can see, the title of the talk, the today's discussion is about photonic topological materials, and I'll discuss in detail what I mean by this. As Professor Mukti said, I just joined IIC in September last year, and we are building an ultra-fast photonics laboratory here, and to work in this domain, actually, photonics and condensed matter physics. So photonic topological material, it's a broad area. So let me be a little more specific. Okay. So by photonic materials or photonic networks, I mean these are basically waveguide based devices. So as you can see here, I'm showing a cartoon of a device. These pipe-like structures, they are basically can guide optical wave. They can guide electromagnetic waves in the visible or IR wavelength range. So they are designed for a certain wavelength. So say 1 micron, for example. And they are also evanescently coupled, meaning if you launch light, it can tunnel to its nearest neighbor, just like what we read in quantum mechanics, like tunneling of a particle from one potential wave to another potential wave. You can also see that I am deliberately moving or changing the paths of these waveguides, right? And they are done in a very precise manner, and also periodically in X, Y, and Z, like in a three-dimensional manner. You change the paths of these waveguides, and if you do that correctly, you can actually realize a topological material. So what is a topological material? I will formally define what it is, but before that, I want to tell you that if you have a topological insulator or topological material, then you can have these robust edge modes, as you can see in this animation. Have modes or states which live on the edge, only on the edge, and they can propagate one way, and they are not scattered by defects or disorder. So as you can see, this corner or these red circles here, they act as a defect. but there is nothing going in the opposite direction. It's unidirectional flow of light, or if you think about electronic system, you can say current. Um, so this is basically what we are going to discuss. And so far, what I'm talking about is linear physics or single particle physics. We'll also see what happens if you introduce mean field type interactions or nonlinearity. And I'll discuss the models and our numerical results as well as the experiments. So so I will take certain so if a few steps from all these papers actually, and these were done in 2 different places. So these first 2 experiments, it's about the fabrication process and a type of topological insulator which we call anomalous Floquet topological insulator. Floquet means that the Hamiltonian is time periodic. So this part is basically taken from these 2 papers, and the experiments were done at Heriot-Watt University during my postdoc. The last part, which is about this interaction or nonlinearity in topological systems and solitons and its propagation. So this part was done at the Pennsylvania State University in collaboration with Mikhail Rexman. So let me also acknowledge my collaborators, Dr. now Professor Robert Thompson, my PhD advisor. Nathan Goldman is a theorist from University Libre de Brussels in Belgium. Patrick Weber, a theorist from Heriot-Watt. Erika Anderson, she's also a theorist from Heriot-Watt. Manuel Valiente, Alexander Spranklin. So Manuel was a postdoc at that time, and Alexander Spranklin, at the time he was a PhD student, and now he's working in industry in Edinburgh. Also, there is Hari Kumar. He's a postdoc now in Edinburgh. So okay, so with this introduction, let's try to understand what's the topological insulator. Okay, so these are a family of material with insulating bulk and conducting boundary states. So if you think about a 2-dimensional electronic material, then this middle part, this bulk is insulating, but you can find one-way propagating states which live on the boundary or on the edge in this case for a 2-dimensional material. You can also understand this from the band structure. So this is a typical band structure of a topological insulator. So as I said, there should be a well-defined band gap, and this is why I said it's insulating in the bulk. But you also note there leaves these states connecting these 2 bands, and the group velocity is finite at all k values. So these are basically the edge states, okay? And I also, here I mentioned that they are backscatter free, and you should see topologically robust edge transport. What does that mean? That means if you have a disorder or defect or a dopant, or if you have a corner, they do not go in the opposite direction. So what is not allowed, propagation in the opposite direction, like in this direction, that's not allowed, okay? And you can also understand that from this band structure. So you can see at these energy values in the gap, there is no state available which propagates in the opposite direction. So there is so as long as the defect or disorder, its energy is within this band gap, it cannot scatter into any other state. So this is why it's not possible to backscatter. Let's take a few more moments and understand it in more details. Why do we see this robust transport? To understand that, let's consider a very simple model. We have these atoms, and we have a big defect in the middle. Okay, it's just a sketch. Okay. Now, if you solve so Vx is basically the potential, and this is the defect or disorder, basically a potential barrier. Now, if you solve the Schrödinger equation, you can show that if there is a wave moving along the positive x direction, then when it encounters this defect, a certain part will be reflected and the rest will be transmitted in general. Okay, and the reflectance and transmissions will depend on the details of this potential barrier and the energy of this, and there are many other details which you need to consider. But for a topological insulator, we know that this reflected channel is not allowed, right? That's why we have 100% transmission. Now, in the Schrödinger equation, because of the time reversal symmetry, we know that if you found a solution moving in the positive x direction, there is also a solution moving in the negative x direction. So to stop this solution which is moving in the opposite direction, the reflected channel, you need to break time reversal symmetry. And this was actually first done in a condensed matter experiment. It's a very famous experiment of integer quantum Hall effect, for which Professor Klitzing won the Nobel Prize. So what is happening here? It's I believe all of you, or at least most of you, have done this experiment of classical Hall effect in your in Calcutta University. When I was a student, this was in our BSc class. So basically, you measure. So we used to measure Hall voltage and all these things. So in this experiment, what they're doing, they're measuring the resistivity. So this is basically this is the classic Hall experiment. I'm not going into details. So when the magnetic field, so they're plotting it as a function of the magnetic field. So at low magnetic field, you do see the classical behavior. So you see this linear behavior. But as you increase the strength of the magnetic field, you reach the quantum regime, and you see that these plateaus, and they're extremely robust. What do I mean by that? So in any experiment, you will always find some noise, right? You measure the data 100 times, and there will be a noise. You can find a mean value and the standard deviation of the measured value. But these points are extremely robust. So the noise is almost nothing in this case. So they thought, when they unexpectedly discovered that, and they found this will be probably used for metrology. So for example, and now it is actually used for measuring, very precisely measuring resistivity. So that, and you can see that from the title of the paper. But later, when theorists like Thouless and others, they elaborated and explained that these plateaus, actually, they have topological origin. So these are basically different topological phases, and this jump is associated with the topological phase transition. Let's discuss that. I'll discuss that in the coming slides, but and of course in the photonic context. But so this was, of course, done in the electronic system, in the condensed matter system, and you can ask, is this phenomena unique to electrons or electronic system? And the answer is no. And in 2008, Raghu and Halden, they actually proposed, they proposed a model, and they showed that the topological robustness, topologically robust age states can also, you can also find them with electromagnetic waves, for example. So this could be light in the visible wavelength, or microwaves, right? And following this suggestion, in the next year, actually, so a group in the US, Marin Solecki's group, they actually demonstrated topologically robust age transport for electromagnetic wave. And this was the experiment, the schematic of the experiment. It was done in the microwave regime. And what is happening here, these are basically a material which is, it's a magneto-optic or gyromagnetic material. So they have some magnetic response. That you can think about Faraday effects. You can see the size of the system. It's like the lattice constant is approximately 4 centimeter. And so there is a metal bar here, which is basically acting as a defect. And what they observe, the lower the part is basically simulation. It shows that you can find these you can actually excite these age states, which are not scattered by this metal rod, this defect. So in the usual case, you would expect some wave moving in the opposite direction, and this is what you don't see there. So basically, they measure. So there is a source here, and there is an antenna here, like a detector, and they measure the transmission. And almost there is no effect of this defect. It's also possible to observe topological behavior, topological age states in the optical domain. So this is an experiment which was done using these helical waveguides. So you basically change the system in time. So these are optical waveguides, but each one, instead of straight optical waveguides, the entire system is basically moving helically, and they observe these age states. So light was launched here around 630 nanometer wavelength, that is the red light, and you see it's moving this way. one way. There is nothing going in the opposite direction. So I'll be talking about actually photonic system, which is very similar to this one, and my working wavelength is actually in the infrared, like 1 micron. Now we have actually many different experimental platforms where you can study topological physics, like the ultra cold atoms, mechanical systems, circuits like LCR circuits, and exciton polaritons, and so on. Now let's also, before we discuss other details, let's try to understand why should we care, and why should we why the photonic platform is so important. Like, why should we study and invest time and money in this photonic platform? So first reason is you can study novel physics, and in many situations you can realize experimentally realize something that is inaccessible in any other experimental platform. It's a very clean system, and you can design your Hamiltonian and realize in experiments. You can study the evolution of the state you want, which, if you think about electronic system, could be very difficult. And as you will see in the coming slide, you can actually measure the evolution of the wave function, and that's a very good and that's a very promising and plus point for this platform. These are some key advantages of photonic system. As I said, it's a very clean system. You can have controllable disorder. You can have controllable interactions like this. This is mean field type interactions. You can have loss and gain, meaning you can study non-Hermitian physics and open systems, for example. You can also have entangled photons, for example. So you can study the behavior of non-classical light or quantum behavior in these networks. And all these things you can do at room temperature. This is an extra advantage, I would say. So the idea or the goal of this field is probably, you can say that, so you can study fundamental physics, and there is also potential device application, and you can improve optical devices with like linear, nonlinear, and quantum optical devices using topological robustness, which you have seen in the previous slides. And I have here noted a few applications like optical isolators, robust optical delay lines, and topological insulator lasers. So the topological insulator lasers is at the moment is gaining huge interest in the community, and people are actually trying to find out what they can offer, which we cannot see in the traditional lasers which we have at the moment. Okay, so in this talk, as I said, we'll be discussing these waveguide-based photonic topological insulators, and I have given you a flavor of this field. Why should we care about photonic platform, and what are these topological insulators? And and now I want to tell you how we can actually create these waveguide-based devices and photonic topological insulators. And there are, as you will know probably, there are many different ways you can make optical waveguides. So the most familiar one is fiber drawing technique. So in CGCRI Kolkata, there is it's available, and I mean, if you think about other places like University of Bath, they have very nice fiber drawing system. And also there is photolithography, photorefractive crystals, and many other techniques. But all these techniques, they have also, they are good for something, but there is also a minus side. And so if you think about the type of device we want to make, where I want to move my waveguide in XYZ in the way I want, in a desired manner. So for that purpose, the most powerful and unique technique is femtosecond laser writing. So fiber drawing technique, if you, for example, here, the inter waveguide spacing, you cannot change. So when you draw the fiber, if it's a multi-core fiber, the cores are always separated by a fixed amount. So making or realizing a Floquet system where you are changing the Hamiltonian time periodically, it's very difficult in a fiber, with fibers. Probably you can do a few things, but not everything we want to do. So why this is so unique? It's because of two reasons. As I just explained, you can make 3D structures, and also you can modulate the system dynamically. You can modulate the Hamiltonian of the system time periodically, for example. Okay. So this is the laser writing. This is a slide for laser writing technique. It's a schematic of the process. So what we do, we focus femtosecond laser pulses. So what's femtosecond laser pulse? So basically these are these lasers. They emit pulses and light pulses, and the width of each pulse is approximately something like 250 femtosecond. This is basically sub picosecond, so below 1 picosecond. And the repetition rate is approximately 500 kilohertz we used, and the central wavelength is around 1 micron, 1.03 nanometer. So we focus these laser pulses, and you need to choose the right parameters. If you do, I'm not going into details, but if you do that, you can change the refractive index near the focus. Okay, and the type of substrate we use, for example, fused silica or borosilicate glass, you can actually change in refractive index, which occurs only near the focus, and this is because of the nonlinear absorption processes. And this is enough actually. And to make an optical waveguide, what we do, we simply translate this substrate in a very precise and delicate manner, and also in a three-dimensional path. And if you do that, you can have this structure with increased refractive index. Now, you know that if you have, inside a glass material, if you have a region with increased refractive index, that will act as the core of an optical waveguide. So it can guide light through this. You can bring two waveguides close, and then you can have evanescent tunneling. It's basically like hopping from one side to another side. So we can make optical waveguides, and as I said, it's a three-dimensional technology. It's also material flexible. You can make waveguides in a wide variety of materials. So if, for example, there are applications like if you want to make photonic devices for 3.4 micron wavelength, for example. So this has application in astronomy. So their optical fibers doesn't work, because optical fibers usually they work up to 2 micron. If you want to, for example, detect Earth-like planet, and you want to make these devices which works at 3.4 micron or 10 micron, for example, then you need to use a technique like this, and this is the uniqueness of this technique. Here I'm showing the schematic, the cross section of a single optical waveguide, so that you can guess or at least have some idea about the size of each waveguide. So this is roughly 3 micron by 5 micron. This is basic. This is not the refractive index profile. It's just the micrograph showing that there is a structure here, and the approximate dimension is 3 by 5 micron. This is the mode profile. It's the fundamental mode. If you are from a condensed matter background, you can think this as the s orbital of an electron. So it has this elliptical shape, close to elliptical. And so the major axis is approximately 10 micron, and this one is approximately 8 to 9 micron. And this schematic I have shown just to highlight again that this is a three-dimensional technique, and we can move these waveguides in a three-dimensional manner. So here I have a movie. This was actually taken at Heriot-Watt, and we are actually building this technology in our lab here. We have started the process here. So this will show you this laser writing process, how we move these stages. So this is a very, very delicate and high precision stages with nanometers precision. And also repeatability and stability. And this is the lens basically, which I have shown here. It's 0.4 NA lens. And if your eyesight is good, you can also see the spot here, the laser spot. With bare eye, you can't see it, but your mobile camera is actually sensitive to IR. So it can actually detect this 1.03 nanometer wavelength. So here you are seeing a circular motion basically. I wanted to highlight that you can have any motion, basically, any motion you want here. Okay, good. So laser writing technique also, it has other applications, like you can make devices for microfluidics and optofluidic devices using this. So after laser writing, if you dip the sample in HF, you can selectively etch, and you can make these micron size devices, which has application, for example, in clinical optics, medical science, for sensing and others. Recently, this is data storage. It's a recent development. So Microsoft is building actually. They are building these laser written structure which you can use for data storage. So you can say, okay, why? why is this so important? Because I can use my USB stick, for example, to store data. But they are talking about, so they are saying that you can store data for thousands of years because you are making some structure inside glass, and we know that glass can exist without any problem for many, many years. Now that number, I got it from Microsoft website, so I don't know how reliable that, but they are saying so that you can store data for thousands of years. And in fact, recently they have stored and read out a classic Superman movie, which is something like 76 gigabyte in this 7 centimeter by 7 centimeter by 2 millimeter piece of glass. And instead of pixels, they have these voxels. These are basically laser written structures. So the point I'm trying to make here, what I'm trying to convince you, that laser written structure is not only important for academic research, what we do, it also has huge application in industry. And this is happening, of course, in US, but I'm pretty sure that very soon, probably in India as well, we'll be making devices, not this one, but something which will be good for daily our civilization and daily life, probably. Okay, so with that background and introduction, let me tell you about our experimental platforms. Let's get back to our photonic lattices. So by photonic lattice, I mean these periodic arrays of optical waveguides. So here I'm showing you a photonic square lattice. So you can see the cross section looks like a finite square lattice, and each side is basically a straight optical waveguide. Meaning, if you launch light here in the middle, it will tunnel to its nearest neighbor, and you will see basically the propagation of light and its evolution along the propagation distance z. So starting from Maxwell's equation, you can show that this evolution of light is governed by this equation here. So here z is, as I said, propagation distance. K naught is the free space wave vector. It's 2 pi over lambda, where lambda is the wavelength of light. And delta n is the refractive index contrast. So nxy is the cross-sectional refractive index. So at the moment, I'm considering that n doesn't depend on z. And n naught is the average refractive index, so delta n is the index contrast. And psi is basically the slowly varying amplitude of the electric field. It is a function of x, y, z. Now, if you look at this expression, this equation carefully, you will very soon realize that this is something familiar to us. It's just like our Schrödinger equation. The only exception is that instead of time, we have z here, right? So here you can say that this equation is analogous to the Schrödinger equation, and z is basically analogous to time. And this slowly varying amplitude of the electric field psi is like our wave function. And minus k naught times delta n acts as an effective potential for light wave. So if delta n is periodic, we have a periodic potential for light. So meaning we have a crystal. If you have a system like this, it's basically crystal, a two-dimensional crystal for light waves. Okay, and here, as I said, the waveguides are evanescently coupled, meaning the state in one potential well has a very small overlap with the nearest neighbor. And if you remember this, the solid state course, this is what we discuss when we study tight binding model. So basically, these are in optics we say coupled mode theory. In condensed matter they call it tight binding theory. It's basically the same. At the moment, it's all single particle physics, by the way. So in this animation now, I'm going to show you what happens if you launch light in the middle and let it evolve as a function of propagation distance. I'm going to show you mod psi, the evolution of mod psi square, and that would be analogous to measuring the optical intensity. So as you can see here, light is tunneling to the nearest neighbor and then the next nearest neighbor. And this is in optics, this is known as discrete diffraction. So you have a discrete lattice and a discrete system like a photonic lattice, and what you observe is discrete diffraction. So, this evolution of light waves is, let me highlight again, this is mathematically equivalent of placing an electron here and let it evolve. And imagine you are measuring the wave function as a function of time. So this basically you can access in this platform. So this you can tell an experimental simulation or quantum simulation if you like. But I guess you understand what I'm trying to say. In this case, in this particular case, I said that I am considering n of xy, meaning the refractive index is independent of z. So this is analogous. This we can say it's a static system, meaning the Hamiltonian of the system doesn't depend on the analogous time, right? But the most very interesting things happen when you modulate the system in time. So when you have modulation in Z, and in particular, we are interested in time periodic modulation, which is known as Floquet engineering. And this would be the topic that I'm going to explain to you. So I'm going to tell you about anomalous Floquet topological insulator. Floquet meaning the system is time periodic. And we use time periodic system to effectively break the time reversal symmetry so that we can have topologically non-trivial bands. Okay. So in a trivial lattice, so before we discuss that, let me tell you what you can expect from the coming 3-4 slides or maybe 5 slides. So if you have a trivial lattice, so I'm not highlighting the lattice size, but it's basically like this, a square lattice. So if you have a trivial lattice, you will, and imagine I'm launching light on the edge. So if you let it evolve, so this animation shows what you can see. So this is basically numerical simulation. You are launching light here, it moves everywhere, it goes in all directions, right? So it's a discrete diffraction on the edge, basically. So the lattice is like this. I'm not showing the lattice size here. If you have a topological lattice on the other hand, and if you launch light here, and if you excite the edge states efficiently, you will see that the light is moving only along the edge. There won't be anything going inside the bulk. And this is one-way propagation. There will be no light moving in the opposite direction. And this is what we will see in the coming slides. So why we are calling this anomalous? This is something I'm going to explain. It means that the standard bulk topological invariants are 0, and still you see topological edge strength, and you'll find out why so. Okay. So after the so we all I think safely assume that we all know the traditional band theory. So if you think about introduction to solid state physics, Kittel or Descartes, what you read, I'm talking about that. So so basically every band. So if we know the band index and the moment, and so you can use the band index and quasi momentum to specify every band, right? But after the invention or discovery of integer quantum Hall effect and the theoretical development after that, we realized that the band theory we study in our bachelor's, BSc or master degree, that's not, there is something incomplete, and there is something which you need to add there, and this is basically the idea of topological invariant. So every band, every block band should be actually associated with a topological invariant. These are integer numbers. So what are they? Let me explain. So for a static system, the standard topological invariant is known as the Chern number. Okay, and in non-zero, so physically a non-zero Chern number implies that there will be some topologically robust edge states if you consider a finite system. So first, if you think about an infinite system, you can get these band structures and the topological invariant. There are ways numerically calculate and sometimes analytically calculate these numbers, these quantized numbers. And if you know this number, so this is known as bulk boundary correspondence, and this is something Ricardo Diaz was also explaining the other day for a lower dimensional system, like one-dimensional system. But basically the idea is the same. So if you know the Chern number of a band, so for example, this is +1 for this upper band, this is equal to the number of edge channel below the band minus number of edge channel above the band. So this is what I have written here. So the Chern number of this band is 1 minus 0, which is 1. Okay. On the other hand, for this band, it's 0 minus 1, which is minus 1. So this Chern number can tell you how many edge channels are there in the system. So if you have a finite system, then it can tell you about what's going to happen on the edge. So basically, you are calculating some quantity using using an infinite system that is defined for the band, but it can tell you the properties if you have a finite system. So what is going to happen on the edge? Okay, I guess if you have any questions, you can ask. By the way, so another thing I want to highlight here. So because so for a static system, because we have translational, so the lattice is this periodic in space. we have quasi-momentum, right? So basically, plus pi by a and minus pi by a is the same if a is the lattice constant. So basically, this band structure is like a cylinder. I guess you know about this. If you have a time periodic system, the system which is modulated in time, something like this. So let me get my laser pointer. Something like this, where your system, so Z is basically time you can think about. So I'm writing Z because this is true for our photonic system, propagation system. But you have a system which has a periodicity of Z naught. So in this case, because of the periodicity in time, energy becomes periodic. And this is why we call, instead of energy, we call it quasi-energy. So instead of momentum, you have quasi-momentum. Instead of energy, you have quasi-energy. And it's periodic. So omega is basically the driving frequency. Now this band structure, so if this is a cylinder, now you have to connect this edge and this side and that side, and then you basically you have a donut, right? Now so I'm explaining probably too many things here, but my goal is to convince you that in a periodically driven system, you can have this situation where the standard topological invariants are 0, but you still have topologically robust state states, and that's why it's called anomalous. So what I have told you so far, that if I know the Chern number, I know the topology of the system and how many edge states are there. Now, if the Chern number is 0, you would guess that the number of edge states will be 0. There won't be any edge states. But because of the periodicity of this Floquet system, you can have this situation. You can have this following situation. So you have this chiral edge state in the gap centered around 0. You can also have another edge band which is connecting these, which is basically traveling across this plus minus omega over 2 and basically connecting the band from the other side. So if you think about this band, this upper, apparently looking upper band, then the Chern number is 1 minus 1, which is 0. For the lower one as well, it's 1 minus 1, 0. So you have a system for which the bulk bands are, it looks like the bands are topologically trivial, but it's not, because these modes they have the properties of these are topologically protected edge states. So actually this problem was highlighted and first proposed in this paper in 2010 by Kitagawa and his colleagues. And in 2013, Rudner and his colleagues, they basically solved this issue, and they said that you need a distinct topological invariant for a periodically driven system, and this is known as the Floquet winding number. Okay, without going into too much details, I think I have convinced you what is a topological insulator. I mean, how the band structure looks like. And if you have a periodically driven system, you can arise to this scenario where the Chern number or the standard topological invariant for the bulk bands are 0, but you still see these topological edge states. And this is simply because you just need a different topological invariant. This winding number, which is physically means the number of edge state in a certain gap. So for example, in this case, it should be 1 for this gap and also 1 for the other gap. Okay, good. So let me now tell you about this model we realized in the experiment. Okay. So for a static model, so imagine you have an electron here. Usually you will have, so this is square lattice. You can assume, so you know that that it can hop to its nearest neighbor. And this probability of hopping, I call it J. It is uniform, so it can move in any of these 4 nearest neighbors. So at the moment, I'm considering a tight binding model with nearest neighbor tight binding model. Okay. So this is the case of a static system. Now I am saying that I want to change the system periodically, but how am I going to do that? I want to change this hopping amplitude or the evanescent tunneling, whatever you call, in a periodic manner. So there are 4 steps in the driving protocol, and in the first step, only these blue bonds are on, step 1. In step 2, this yellowish or orange bond, and step 3, green bond, and step 4, the brown color bond. So let me play it so let me slow it down. So in the beginning, only J1, and then J2, and J3, and J4. So you see, it's a clockwise manner. I'm switching on and off in a clockwise manner. So let me try it. Let me play it again. Okay. So this is how I am switching on and switching off these bonds. Okay, if you think about a condensed matter experiment, is it possible? It is impossible, okay, to do this. Or maybe it will be possible in the future. At the moment, it's impossible. But I will show you with photonics, this is something you can do. You can realize a model like that. Okay, now I am going. So this is as you will see that if you do this within certain parameter space, you can realize a Floquet topological insulator. But let me take the limiting case, which is the simplest one. So what is that? So I am assuming that when a certain bond is on, and if I place a particle here, say an electron or a photon, the particle will, the probability of hopping is 100%. So when the bond switch off, you will find the particle here, right? So mathematically, this means J times T over 4. This is the duration for which the bond is on. This is pi by 2. So this means the probability is basically 100%. And let's see what happens. So imagine the particle is here. So if you do that, you can see, you can follow the links basically. And so what you have just seen is after a complete period, meaning after 4 steps, you will see the particle comes here. So two, basically, that's one lattice constant, means 2 spacing basically. So one state, in the second it will wait there, in the third it will move again. Okay, this is, as I said, this is a very simple situation. You can deviate from there. And the nice thing about topological insulator is even if you, as long as you don't close the band gap, you will see the topological edge state. So here I have a missing site, which means so there it's deliberately not there, and it's you can see it's just moving. The state is traveling around the defect or the missing waveguide here. On the other hand, if you look at the bulk site, if the particle is here, after every complete period, it's coming back to itself. It means that the evolution operator is unitary, basically, in this case. Okay, so I think I have told you about this model and have shown you some animation so that you can understand it quickly, what's happening here. This is the experimental realization. So we use these synchronously bent optical waveguides to switch on and switch off these bonds. And this is the band structure. Now, as I said, in this case, I was showing you the simplest situation, but you can basically you can have some other value as well. So, for example, pi by 2 times 1.2, for example. And in this case, these are the 8 states propagating one. This is a lattice we fabricated in the experiment. So let me show you the experimental results. I think I have at least 15 minutes, right? Okay. So this, what you see here is okay. So this was the experimentally fabricated lattice. So these white dots, basically, they are the core of the these are the cores of the optical waveguides, right? And this is the input facet, by the way. And here, what I'm showing you the output intensity distribution. That's basically mod psi square after a propagation of 70 millimeter. And these white circles it's basically guide to the eyes, okay? And they basically indicate the lattice sites, okay? And this red square tells you where I am injecting light at the input. So light was injected here at the input at time t equals to 0 or z equals to 0. And after the propagation of 70 millimeter, you see it's moving by two spacing, meaning this is basically one lattice constant. Okay, this is after 140 millimeter, and it hits the corner. If it's not a topological insulator, you would expect something moving in the backward direction. But that doesn't happen here. You see, it's moving around the corner, and now it's hitting the defect, the missing waveguide, which was not fabricated deliberately, and it's passing the defect. So you see almost no bulk penetration. It's because we are exciting the edge state very efficiently, something like 88% or 90% or something like that. So there is some excitation or some overlap with the bulk state, but it's very small, something like 10 to 12%. We see one-way transport and no backscattering, basically. So what I have just told you, so this is an experimental demonstration of a photonic Floquet topological insulator, and to be more precise, it's basically an anomalous Floquet topological insulator. So this was published in this paper, 2017 paper, and this detection method, we have used a very novel detection method, which I'm not going to tell you in detail, but it's also interesting. So what we do, we basically place the system inside a cavity. So you launch your desired state, and at the output, a certain fraction you detect, and the rest you recycle. So this basically, this effectively increase the evolution time, because the lattices we make, they have a certain length. You cannot make a photonic lattice which is a kilometer long or something. So usually these are like 10 centimeters long. So if you want to probe long time scale effects, this is the way you can do. You can place it inside a cavity and recycle. So this we call state recycling and time resolved imaging. Okay, so this I have told you briefly, and let me switch to the new topic, which is about optical nonlinearity and interacting. You can call interacting topological photonics. So far we were discussing about linear physics, meaning single particle physics. You can always ask what's about particle interaction. What happens if you switch on the interaction between the or among the particles. Now we know photons do not interact, right? They usually don't like to talk to each other. They propagate independently. But you can have some effective interaction if you have very high optical intensity, and this is known as optical Carr effect. So this is basically the Schrödinger equation with this additional term. So this is basically the linear part of the Hamiltonian. And this nonlinear part, it arises because of optical Carr effect, which is an instantaneous effect. It's an electronic effect. It's mod phi a square. You can see it's intensity dependent, right? I would also like to highlight that this equation, mathematically, it's the same as the Gross-Kitaisky equation we used to explain bosonic interaction in a Bose-Einstein condensate, for example. So what I'm trying to convince you, the results I'm going to present, they are very general. They are actually applicable to a wide variety of bosonic system, not just photons in our optical waveguides. Okay, so when you have this term present, what you can study? There are many things like modulation instability and four-way mixing and many other stuffs. But perhaps the most exciting thing would be to study optical solitons. And this is what I'm going to tell you. So what are solitons? Let me define what are and tell you what are solitons. These are waves that propagate without changing shape as a result of nonlinearity. Now, if you think about waves, any like light, sound, so usually they have this tendency to diffract or disperse, right? So if you think about a wave packet, as you propagate, because of the velocity dispersion, it will spread. If you have nonlinearity in your equation, in your differential equation, this nonlinearity can, in certain conditions, balance the spreading. So you can end up with having a wave packet which doesn't change its shape as it propagates, and this is known as a soliton. There are many other definitions, so you can also define it this way. It's basically a bound state of a potential created by the state itself, and these two means the same basically. Okay, so let me go back to the previous slide. So these solitons are being studied for a very, very long time. So first experiment, it's 1845 by J.S. Russell. And this was done, this experiment was done in water waves, formation of solitons. This is the canal in Scotland, and you will be, you shouldn't be surprised actually, but I used to live near this canal, by the way. And so they did this, so he observed something long time back, and he reported it, and then since then it has been studied in many different fields: optics, plasmas, fluid mechanics, condensed matter physics, to name a few. Also ultra cold atoms, bosonic systems. And this is basically the first experimental demonstration of a soliton in an optical waveguide array. So you see the diffraction, linear diffraction, when the power is small, when this term is small. As you increase the nonlinearity, strength of nonlinearity, you see formation of a soliton. But these are in a static system. So what we are going to discuss, solitons in a Floquet topological insulator, in a time periodic system. Okay, so let's try to understand that. So in the recent past, so starting in 2013, there are actually a few theoretical proposals. So how you can realize solitons in a topological material. So the most interesting one, and probably the important one, is the first one by Loomer, 2013. They talk about bulk solitons, meaning soliton formation in the bulk of a photonic topological insulator. Also, there are age dynamics. So this is Mark Ablois, a very famous mathematician. And also there is this paper by Daniel Leakham in 2016. So these are the literature, most important literature. And in all these papers, they have considered these helical waveguide arrays and how you can realize bulk and edge solitons there. I'm going to consider our previous model, this anomalous Floquet topological insulators with these 4 steps driving protocol. And I didn't mention in the previous slide. So you can define this parameter lambda, and you can show that this model is topological in this window. Okay. So you can actually, if you tune the hopping strength, you can see a topological phase transition here. So in the first step, we confirm that it's a topological material by detecting these edge states. So if you launch light here, it moves. This is the upper edge. It moves this way. So if you launch light on the upper edge, it moves this way. If you on the bottom edge, it moves the other way, right? That's what it should happen. That's what is expected actually. Okay. So we use a numerical method, which is known as self-consistency method. So the idea is to iteratively calculate a soliton solution. Okay, and you start with a gauge solution, and you introduce this nonlinear term, and you end up getting a solution of this nonlinear Schrodinger equation. This is a nonlinear. It's like a nonlinear eigenstate. Okay, and for our lattice model, we found this type of solution. So I'm showing the dynamics for one complete period, and you can see that it's moving. So it's shape preserving in a Floquet sense, meaning it comes back to itself after each driving period, but within the period, it is allowed to change its shape. Okay. You also see this cyclotron type motion. It's basically rotating. The peak is rotating. So this is, of course, an observation from our numerics, and we actually calculate these solitons as a function of nonlinearity, and we found this family of solitons. Okay, so what is the novelty in terms of like what is the difference from static solitons actually? So let's try to find out. So it is a sketch. So in the static case, the solitons are formed from the linear modes, and as you increase the power or nonlinearity, the energy of the soliton goes downward for the focusing nonlinear, meaning when this sign is minus. It means that a soliton becomes more and more localized as you increase the power or the nonlinearity. And I will show you the experimental results associated with this one. But with our Floquet soliton, it's different. It's again because this axis, the vertical axis, is periodic. So as you increase the power, the soliton family comes back to the linear modes again, and we know when they are close to the linear modes, they are delocalized. So as a function of nonlinearity, for the Floquet system, we expect delocalization to localization to delocalization. Unlike the static case, where you should observe that the localization, it becomes increasing localization as you increase the power. By the way, here I am plotting the spatial extent of the soliton, which is, and I'm quantifying using the inverse participation ratio, which is defined here. It's basically a measure of localization. So if IPR is 1, all the light or all the state is a single site. Okay. This is some calculation using our exact parameters that we used in our experiment, and you do see a peak in the IPR, and this is what we are going to show experimentally. I am not going to tell you too much about the experiments, but there are certain things which are very important to check before you start the experiments. So this is the effect. There is an effect of self-phase modulation. So basically, because of the nonlinear shape of the pulse, you generate new wavelengths. You have to minimize that. You also need to minimize, so basically in our experiment, there is no nonlinear losses. So that we verify that as well. Negligible chromatic dispersion. So basically what I'm trying to say that in our experiment, the state is a function of both Z and time, because we use laser pulses to access nonlinearity. And you need to make sure that you are in a parameter space where this equation is valid. So you are actually simulating this equation in experiments. Okay, so this is the static case. So these are experimental results. Okay, in the left-hand side, I'm showing the output intensity distribution. So I'm launching light here at this arrow, and you see it's diffracts. On the right-hand side, I'm plotting the IPR as a function of input power. So let's see what happens as I increase the power. Okay. So you see, as I increase the power, the state becomes increasingly localized. In the static case, this is a trivial lattice, by the way. Okay, square lattice with uniform hopping. So this experiment. This is a baseline experiment which gives you the confidence that things are working in the experiment, and it shows the formation of highly localized soliton in a standard square lattice, and it also gives us confidence that we have enough nonlinearity to see to probe the Floquet soliton. Okay, so this is for the Floquet soliton. So we are launching light here, and at low power we see a lot of diffraction, which is expected. As we increase the power, you can see that the IPR, it becomes localized, it becomes increasingly localized, and it shows a peak, and then it becomes delocalized again. So this is the key difference from a static lattice. So you see a peak in localization. So you observe, and this is happening because the soliton family is, because it's a Floquet system, basically. It's a time periodic system. So you are expected to see that. Okay. We also observe the cyclotron type motion basically by measuring the intensity after, so this is after 2 driving period, and this is after 1.5 driving period. So you have probably noticed that the most intense side basically moves on these 4 sides. So I have shown it here. You see the most intense side basically moving on these 4 sides. So after each driving period, it comes back to site 1. So after 1.5 driving period, it should be there at site 3. And this is what we observed in the experiment. We launch here, and you observe the most intense site directly across this input excitation. So this tells you that there is this cyclotron type motion. So basically, we prove experimentally check that our model and everything is basically what we expected. Okay, this is not something I'm going to tell you. Okay, so it's another, I will probably finish in 5 minutes. Is that okay if I take another 5 minutes?
Yes, you can take
okay.
5 minutes.
So this is about the age soliton. It's probably the more interesting than the bulk behavior. So as I said, if you consider the linear propagation of a wave packet, as it propagates along the edge, because of the group velocity dispersion, it diffracts. For a topological lattice, in a topological lattice, it remains on the edge, but it spreads. And we are trying to balance this using nonlinearity. So the idea is to use some nonlinearity so that as it propagates, it can, to some extent, at least to some extent, it can maintain its shape. But because of the discreteness of the system, you also expect some radiation into the bulk, and this is basically something you can call mode mixing. So in a linear system, if you excite a set of edge states, you don't have mode mixing, but the nonlinearity can mix edge to edge or edge to bulk states, and this is basically this radiation. So the summary is basically this sort of nonlinear edge states will have a finite lifetime. So they will remain on the edge and maintain its shape up to a certain time. It's basically a very similar model, so I'm not going to discuss that. And let me show you the simulation results. So I'm showing you the dynamics on the edge. So in the linear case, you see it's moving one way, it's showing its topological character, but it's also spreading, as you can see here. If you hit the right power, you can see it's moving almost like a soliton. So it's very little diffraction and also penetration into the bulk, but so this is why we don't call it a soliton. It's soliton. We call it soliton-like edge state. Okay, if you go to higher power, you also again see diffraction. So for a given propagation distance, if I plot the inverse participation ratio or the localization, I should again see a delocalization to localization to delocalization. So we have measured that for 3 sets of parameters, and in all 3 cases we see that behavior. This is the intensity pattern for delta for some parameter, which actually I didn't discuss. So let me tell you briefly. So basically here we are dimerizing the bonds, and this dimerization parameter is delta. It's defined here. So lambda 1, lambda 3 are pi by 2, 1 plus delta and 1 minus delta. Effectively, we are dimerizing the lattice. And so this is the intensity pattern. This is a linear case. You see propagating along the edge. So here I'm launching light in the white circle. And this is the soliton-like state, the most highly localized on one side, and this is a high power. Okay, so the soliton-like state can also walk around a defect, around a corner here, as I've shown here. But please note that whenever it encounters a defect, there can be some excess mode mixing. So it's different from linear states, and this is this more nonlinear mode mixing is actually something you can expect in a nonlinear state. I'm almost I'm done actually. So open questions in the field. So the topology, the interplay of topology, nonlinearity, and disorder, highly untouched territory. People are still thinking about like what can be done, and this is probably the $1 million question. Like we don't know exactly, because these are very these systems are not intuitive at all. In linear system or single particle case, you can guess many things. Here it doesn't work basically. So you need both experiments and theory, and this is basically what I have written here. Topological invariants are also the concept. It's basically linear theory. So in the nonlinear case, how you can define that, nobody knows. Neither theorists nor experimentalists. Quantized observables in nonlinear systems. There has been some observation. We have published one paper with quantized transport in nonlinear systems, but again, not very well understood. So nonlinearity or interaction induced topological phase transition in these bosonic systems. So you can also have something in mind like a fractional quantum Hall effect, which is a fermionic system. So today I have discussed about like bosonic system interaction in bosonic systems. Okay. These are some highlights, like what we are doing at the moment. So we have, okay, let me tell you about our group. So we have 2 PhD students at the moment, Manish, Gayatri, and Rishabh, and we have 2 interns at the moment, Manish and Sidev. We are actively looking for both PhD and postdocs. So if you know anyone interested to do postdocs in this field, basically photonics and condensed matter in topological systems, you can contact me. And there are very prestigious, highly prestigious fellowships, institute fellowship. This is C.V. Raman postdoctoral fellowship and this Institute of Eminence. You can contact me, directly contact me, send me an email with your CV. So, okay, after this, so I have introduced you with our group, and this is basically 2 separate projects. So the first one is realization of synthetic flux in a 2-dimensional lattice. And using this synthetic flux, you can actually have a topological lattice. So this is a different way you can create topological lattice, and you can study Hofstadter spectra in the photonic domain. So these would be more like the quantum Hall-like states in the photonic platform. And we are also interested to do some to study nonlinearity and disorder. So these are some initial simulation Rishabh reproduced. So not reproduced, I should say. I mean, there are some proposals in condensed matter platform. We are basically designing the system with waveguides. So this would be some. These are basically, this is one possible design for the system. So these are basically waveguides which are circularly carving. The refractive index is also changing along the propagation. It's a very complicated system, by the way, and we do see topological states here. Gayatri is actually working on a few different projects. So one of them is basically about these different optical modes, spatial modes. So these are basically you can say higher orbitals. So this is s orbital. This is like px orbitals, and can we switch on the interaction between them, like coupling between them, and what can be studied in higher orbital physics. This is also here doing, and we are very grateful to IISc for startup grant and also ISRO for funding. Okay, so I have discussed femtosecond laser writing. I have given you a brief overview of this field, told you about our fabrication technique, told you about photonic lattices, Fouquet engineering, anomalous Fouquet topological insulator, and nonlinear topological photonics, particularly solitons on the edge and also on the bulk. These are our funders. So basically both projects were funded. So the first 2 were funded by Harriet Watt and SUPA, Scottish University Physics Alliance, and the nonlinear part was actually funded by Penn State and ONR, Office of Naval Research. So thank you very much. If you have questions, I will be very happy to answer.
Thank you, Sebabrata, for your excellent presentation on your pioneering work on topological insulators. And students are eagerly waiting to interact with you via their questions. So there are some questions in the chat box. So let me read this question.
Sure.
So first question is from Moitre Kundu. Is this Schrodinger-like equation applicable only for the photonic square lattice? I mean,
No,
if we
no.
construct a photonic lattice which is not a square lattice, what changes do we need to incorporate the equation?
No equation, no change. So if you think about the equation in the beginning, no, it doesn't have to be a square lattice. So I have shown most of the results with a square lattice, but if you look at this one, it's a honeycomb lattice, like a graphene, you can think about. So there are a lot of models. So what Ricardo was presenting the other day, SSH lattice and H states on the SSH, and this has been, people have demonstrated those. So any two-dimensional lattice you can think about square. I mean, there are five, I think.
Honeycomb lattice, maybe.
Yeah, there are five like Bravia lattice in I think five, right? So you can basically do in 2D and 1D any model. So yeah, that is possible. Totally possible.
The next question is from Tuhin Devnath. Why topological phases arise?
Why topological phases arise? So if you are asking what we are doing to make it topological, that is basically Cloquet engineering, effectively breaking time reversal symmetry. That's why it's arising. So this is what I was explaining in the beginning. If you remember my first couple of slides, so why topological, why these edge states are appearing, because you are basically presenting the reflected channel by breaking time reversals.
One more question from Samrat Rai. The topological properties of photonic or other systems is mostly observed in the linear regime. So can you provide any way to deal with nonlinear regime?
So that's what I discussed. That was the last part of my talk, right? I don't know
Yes.
when they asked actually the question. Maybe in the beginning they were.
No, I think they
Yes,
asked it
maybe.
at the beginning.
It was in the beginning.
Right,
Yeah.
right.
So, and by the way,
That was asked.
I should highlight that this was, so the first experiment I was telling, this Cloquet topology. This is the first observation of the interplay of topology and nonlinearity. Okay. So there are actually now, I think 3 or 4 papers, or maybe 5 papers, and 3 of them are from our group, my previous group basically. And there is also 1 or 2 demonstration from Alex Zamait's group in Germany, Rostock, University of Rostock. So yes, there are a couple of experiments, and so far there is no experiment in ultra cold atoms. But many things we learn from ultra cold atoms, and there are a lot of things they learn from us. So probably they will do something in the coming years.
Amrita Mukherjee is asking, can we call the edge states as topologically protected even if Chern number is 0?
Yes. The Chern. So for the case I said I discussed, it is the Chern number is 0, but you have a different topological, a distinct topological invariant which is non-zero. The winding number is 1. So in this topological, think about the topological class. There are many different topological invariant you can define specific to the system. For example, Ricardo was talking about Zach phase the other day, right? So that's so there you don't discuss Chern number in that case. So it's the Zach phase. This is how people define the topological invariant. So yes, for our case, and this is the beauty of the system. The Chern number is, so the bulk bands apparently they look trivial, but they're not. They're not.
Sushmita Jana is asking, can we get edge states even if the bond length of the square lattice is not equivalent?
I would say it's not clear. Your question is not clear. Maybe you can send me an email with some elaboration. But usually, yes. I mean, imagine you are in a topological phase and you are changing some bonds or adding some on-site energy, or you are perturbing the system somehow. Okay, as long as you don't close the band gap, it remains in the topological phase. That's the beauty of this system.
One question from Shovik. why are we considering only single site excitation for photonic topological experiments?
No,
Is
it's
it
not.
just for beginning with the simple case?
Yes.
Another query, what happens if we tune, suppose increase T very slowly, the driving period of a Floquet topological insulator?
It's very good question. So let me first answer you why single site excitation. Um, it's simple. So when you design all these things, you have to think about what is accessible in the lab, what we can do in simulation, and you have to also think about publication and all these things. You can make use for example spatial light modulator, and this is what we are doing at the moment. So there are situations where we can have some simple we can simplify experimentally. So already the experiments are so complicated. So the single site excitation just makes it it's actually we can handle the situation, and so it's not an excuse basically. So you can so for example the thing I was showing here, so you can prepare states like you can prepare states like this actually, and observe topological. So this one.
Yes, I think actually that is for the experimental purpose, right? Suppose we are considering a square
For
lattice and
experimental purpose as well. I mean, there are situations where a single site excitation is not enough. You have to think about how what is the overlap with the edge and what is the overlap with the bulk state. If
yes,
you
exactly,
right,
exactly.
so there are
About the
situations.
position of that single site, if
So
it
you
is
may
in the
you
edge
may
or
you may encounter a situation where single site excitation is not enough. So in that case, you have to launch light in multiple sites. So we have done that in some experiments. I have not presented it today. And I mean, using SLM, this is possible. Regarding tuning the
time period of the
time period,
topological
or
insulator.
actually it's better not to change the time period, because then you also change the Floquet mass energy, this plus minus omega over 2. But you can change, it's better, you can change omega, but it's better to
The
tune.
frequency, right?
Yeah, but it is better to tune J probably to see a
Okay.
topological transition. You can do that. Actually, we have done that. And in fact, some cases you can just tune the wavelength of light to change the hopping amplitude, and that will show you a topological transition. So in one case, you will see topological states which are moving one way. In another
Yes.
case, you will see that it's not moving. It's basically penetrating the bulb.
And there is a topological phase transition in that.
And so
Okay. Great. Great. Thank you.
Question from Shomodip. What may be the practical example of the waves are balanced by the nonlinear constraints, as you said in solitons?
So probably the most famous one I can say is would be tsunami probably. So you see when in these water waves, so when so there are many reasons, and you can read on you can search Google it and then find out. But tsunami is an example actually of these solitons, where so they propagate very long distance with very little change in shape, and these huge water waves, and it's basically it's a soliton. It's basically a soliton. Also, in optics and plasma, you will find many examples actually where the diffraction in water waves, if you throw a rock, it's not a soliton, right? It diffracts. But the example I just gave you, the tsunami, a wave in tsunami, it doesn't change too much, and it propagates very long distance. So that is one example. There are many others.
Yeah. Can I just make a single comment? A comment is made for Somadip actually. Somadip, you just search in Google. There is something called rogue waves.
Yeah,
Rogue
rogue.
waves, yes,
Rogue waves
yes.
that sink ships. Okay, so if you just have a look at them, it's fascinating physics.
Yeah.
Yes. So one more question from Shamrat. Why does most localized states lies on the middle? Can we relate it with statistical reason?
I didn't understand the question. So
Why does most localized states lie on the middle?
Okay.
You
So,
shown a graph between
So,
delocalized and delocalized. Localized states are lying on the middle. You showed a plot. Maybe in the last 4 to 5 slides.
this one
Yeah,
you are talking about, right? Yeah. So why is it in the middle? So basically these solitons mostly they so if you think about the envelope, it's usually in many cases, not probably this case, but basically it's a single hump envelope. So if you think about a one-dimensional continuum case, it is basically a sec function. That is probably one reason it's in the middle. So what what is your other guess? I don't get it. Right?
Okay. Fine.
No, so are you saying that there?
I also asked about the third plot. If you go to the shift to the right side of your slides, see, this one only, this slide,
Right.
the plot of the special extension.
Okay. That is a good question actually. So, okay, why we see the peak here, right? So that's a very
Yeah.
So okay, uh, so it is known, and we can show that numerically and analytically that when associated with the mid gap cross energy. It's something like what is it? So 1 point, I know. So 0.11 or 0.12 or something. You see, that's the value.
Okay, thank you.
So, right. Okay.
And this is a compliment from Arunahoda. Fascinating talk, Sheba, inspired.
Thank you.
And last question, maybe. So, question from YouTube. What are the use of such waveguides?
Many. So if you think about only topological case, so I actually wrote somewhere, I don't remember. So there is right now at the, there's a big, okay, I can give you a very philosophical answer, bro. That's better instead of going to the nitty-gritty details. So topological lasers is a big thing at the moment. So we don't work on that particular domain at the moment, but maybe in the coming years we will do. So basically the idea is, so if you think about one waveguide or one fiber and you are making a laser, so the lasing core is basically one core. If you go higher power, so at the moment we have very high power lasers, but there is no limit, right? You can go to much higher power, and people are asking what we have to do to go to much higher power. It seems that you need to break or you need to channel light in multiple cores, otherwise the fiber will be damaged. Now, if you want to channel light in multiple cores, there is something called Anderson localization. Because these cores are not uniform, so because of the disorder, you see some modes is one mode is localized at this position, another one is in a slightly different position. So you don't see a coherent lasing property. What topological lasers can give you, it's light is in multiple age waveguides, but it's one mode, one eigenstate. So even if you have disorder, you won't see Anderson localization, and you can get this lasing mode. This has been experimentally demonstrated, and people are still working on that. That's one example. We also, so what is unique about topological insulator? The uniqueness is the robustness against defect. Even if you perturb the system, the light or the state is propagating one way, no backscattering. That's the uniqueness. Now, you might know that at the moment, the government of India is spending so much money on quantum technology. It's not government of India only. It was started from China, UK, Europe, US, every country. And why so? There are many reasons. You can Google it. Now, I'm going to tell you about the fundamental physics. So imagine you have two entangled photon pairs or entangled states, and you want to send it. So, for example, I want to send it from Bangalore to Kolkata, right? Now, if you are going to use fiber channels, for example, because of perturbation or so environmental effects, or maybe there's a storm somewhere, the question is how much perturbation the entangled pairs can withstand. After a certain point, or maybe if you add some perturbation, it won't be entangled anymore. So that's a problem, right? If you want to implement it, this is a problem. So we can actually help there. We know that photonic topological insulator, there are robustness. There is a robustness. So small up to a certain limit, if you perturb the system, you can protect the entangled photon pairs. So this has been actually proposed and shown. So this is another application. So I can go on actually. So I think I have answered your question.
And I do not find any questions in the chat box related to the last question. Can I ask a question to you, Sebabrata?
Sure.
So that is related to the mode of transmission in the waveguide. What kind of mode you are using? It is transverse electric or transverse magnetic?
Sure. So that's a very good question. So the way I have presented, like the Schrodinger equation, Schrodinger-like equation, and all these things. So for these waveguides, in general, you are supposed to consider the Maxwell's equations and solve that thing. But what we use, it's called a scalar wave approximation, meaning what we observe is that the polarization is not rotated. So if you launch vertically polarized light, you get vertically polarized light at the output. So you can call it TE or TM, or these linearly LP modes, linearly polarized mode. It's basically different versions of same story basically. But the good thing is, whatever you launch, it remains. You don't see any rotation of polarization. So in our experiment, I think, for all different experiments, I have used vertically polarized light. So if this is my waveguide structure, it's vertical like this.
So transverse electric.
I think so. Yeah.
Yeah. Okay. So let us thank the speaker for an inspiring lecture. And I would like to hand over the microphone to Shovik Chatterjee for the next session. Thank you, Shiva.
Thank you.
So thank you, sir. And I would like to thank our plenary speaker, Dr. Sebabrata Mukherjee, for this illuminating talk. We all have enjoyed a lot, and sincere thanks on behalf of the team ICCMSP. So as we are running out of time, so I would like to hand over the mic to Moitra Kundu to chair the next session, which includes the 2 oral presentation in the first session of second day. So Moitra, over to you.
Thank you, Shovik. Am I audible?
Yes, you are audible.
Yes, you are audible.
Okay, thanks. So after the fantastic theory talk, we will now have 2 oral presentations in the morning session. Now, each oral presenter will have 15 minutes for their talk, and then there will be a 5-minute question answer session for each talk. So the first talk will be from Mohammad Tanvir Alam from Bhupendranaran Mandal University, Bihar. So you can go ahead and start your presentation.
Hello. Hello.
Yes, you are audible.
Yes.
Audible?
You're audible.
Okay, sir. Thank you. Is my visual PPT? Hello.
You're audible.
So my PPT is visible?
Not yet. Your PPT is not visible yet.
Your screen is not sharing.
Hello. Hello. Hello.
Hello. Mr. Alam, your screen is not sharing.
PPT. You are telling yes, my is visible, not visible?
Yes, sir. You can share your screen now. We can hear you, but we can't see your presentation.
No, we can tell you what you. Okay. Hello.
Hello. Yes,
Hello,
you
yes.
are audible.
Yes,
Yes,
you can share your screen now.
Screen is visible?
No, it's still not visible.
Not visible. I am presenting here, not visible. Hello.
May I suggest something?
Screen is visible.
Tanvir, you can send a mail with the PDF to ICCMSP and they can probably share the screen.
Okay, okay, okay. Hello.
Yes, we can hear you.
I will try later. You can.
Moitra, I think you can go with the next speaker. He's having some problem, I guess.
Yes, I think that would be better. In that case, we can shift his talk to the second position then. So okay.
Hello, hello.
He's sitting.
Yes, you can tell.
Yes,
I am mail PPT.
You have
Okay,
emailed,
okay,
okay.
mailed it. Okay. Then wait. Just wait.
Shomadip, kindly check and share the.
I am mail.
Yes, Shomadip. Please
We have
share the
not
presentation.
received any mail yet. I think it is taking time for internet issues.
You check.
Please.
Okay,
Maybe
so
check
just
I
let me
accept.
make an announcement. I guess
please.
it will be better if we shift this talk to the second oral presentation, right?
Okay.
So we can reshift the second presentation.
Yes.
That will be better.
Yes, that will be
Okay, so
better, right?
I guess we can go to the next presentation now. So, as planned, the next presentation now will be from Amrita Mukherjee from University of Poland. So, as usual, there are 15 minutes for the talk and then 5 minutes for the session. So, you can start the presentation.
Thank you. Am I audible?
Yes, you are audible.
Okay, let me share my screen. Is it visible?
Yes,
Yes, it's visible.
Okay, thank you. So, shall I start?
Yes,
You can.
Okay, fine. So, good noon, everyone. So, myself, Amrita Mukherjee, I'm going to present my talk on tailoring flat bands and topological phases in a multi-strand cross network. First of all, I'm grateful to ICCMSP for giving me the opportunity to present my talk. Okay. So, at first, before going to the details, we'll shed some light on topological phases and the phase transition. So, these three guys have won the Nobel Prize in 2016 for the remarkable observation regarding topological discoveries of theoretical discoveries of topological phase transitions and topological phases of matter. Okay, these two guys have the main contribution in the topological phases of matter, and these two guys have the main contribution in topological phase transition. At first, we'll talk about what is some metal and insulator. It was for the free electron. This is the familiar dispersion relation, E versus K diagram. This is the periodic lattice. This is the lattice constant, and we know here that all the wave functions are the block states here. For the nearly free electron, there are some gap opens at the Wilson boundary. What is the reason behind this gap opening and the Wilson boundary? Because black reflection occurs at the Wilson boundary. You can see from here the electron, the main electron density will maximum in between these two ions, this one and another one just above the ions. You can see here. One is proportional to sine square part, sine wave and cos wave. That's why the gap opens at the Wilson boundary. Now, what is metal and what is insulator? We will explain it giving the idea of field states. If you take one bottle full of water and you are shaking it, if it is full of water, then even the water can't move here and there, right? And this is for the insulator case. You can see from this field states. And if you take just half filled water bottle and you are shaking it, the water can move from here and there. So it is from half filled states. That means there is metal. Free electrons can move and is insulator. Two electrons means one is for the spin up projections and another is for the spin down projections. Okay, the main the path breaking observation is the quantum Hall effect, which is the main origin of this topological insulator. The 2D electron gas is trapped at very low temperature in uniform magnetic field, and and you can see there's two kind of resistivity. It's longitudinal and the transverse. From the longitudinal resistivity, you can see there is it's zero, whether the transverse is some plateau region. Why the longitudinal resistivity is zero? Because of dissipation less flow of electrons, because Landau levels completely failed and there is no states available for the electron to scatter into, and for the this transverse resistivity in between two Landau levels is the plateau regions is constant, and when we are increasing the magnetic field, that means the electrons are trapped here and they are going to the edges of the material. Okay, you can see that these electrons will just moving around the edges, around the surface of the material. So the new material comes here. This bulk is insulating and the surface is conducting. This is called this topological insulator. Now, what is topology? You can see this picture. There is just continuous deformation or the bending or twisting from this coffee mug to this donut. Both have only one hole here. Is a hole means is a kind genus. So the coffee mug and the donut belongs from the same topological class. But we are not tearing this one. We are remaining, the hole is remaining there. So you can see this glasses, this two holes, and this orange, this ball and the muffin all have the zero genus number, zero hole number. That is the main topology. Without tearing it, just continuous deformation and by bending or twisting. Now, what is topological phase transition? It is not like the familiar phase transition, a spontaneous symmetry breaking, which generates some order parameter, and that follows some Windruck-Landau symmetry breaking theory. But here, there is no kind of symmetry breaking. All symmetry will be protected here. So, I'll just explain it by the schematic diagram. You can see this one have two holes, right? And this one have only one hole. This one has only one hole. You can go from this state, from this one by just closing this gap. You are closing this gap and going from this state to this one. That is, there is a phase transition from this genus to the this one by closing the gap. And during this phase transition, there is one another topological invariant comes there by some drastic change of the invariant. First, the easiest model of topological phase transition is the two-bond model, this Su-Schaefer-Heger model. You can see that, sorry, this one, the two-bond model. So this is the unit cell. It is repeated along the x-axis, and this is the Hamiltonian in the case space. From this relation, we can plot the band diagram, and we can see that this V is the inter-unit cell hopping, and U is the intra-unit cell hopping. When this V is a two-bond model, UV, UV, UV. So V less than U, you can see the gap appears at the Brillouin boundary, and when you just equal U and V, then the band gap closes, and again when V greater than U, band gap again opens up at the boundary. What is the main observation thing here? The Jacques phase. This Jacques phase means some topological invariant we calculate in case of one-dimensional periodic lattices. Before this phase, Jacques phase was 0. This is a trivial case. And when we are going to, after closing the gap, we are going to another one, then we are getting this Jacques phase quantized. That means there is a drastic change of Jacques phase. This is the famous formula of Jacques phase, and this quantized. So there is a topological phase transition occurs here. Okay. Now I will give some outline about my work about this tailoring flat bands and topological phases in Croise network. Where this is the schematic picture of the multi-strand Croise network, the staggering hopping, this UV, 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 they are the cross hopping, and this is the backbone hopping, and this is the vertical coupling. For the simplicity, we are taking only the two-arm ladder network, this one, this is the backbone hopping, this vertical coupling, this is the next nearest hopping. So in this case, this box is the image set. We can write the Hamiltonian in the case space. The main feature of the topological phases is the symmetry protected. So this Hamiltonian has the time reversal symmetry time reversal symmetry protected. It also has the chiral symmetry, and this is the chiral operator, and also exhibits the inversion symmetry. Along this line, this inversion symmetry is projected here. Now, I will talk about the band diagram, the dispersion relation. From the Hamiltonian in the case space, we can plot the bands with respect to K. This is the Brillouin boundary. And we can see for this kind of parameter, V less than U, this is V and this is U. We can see that Jacques phase is 0, trivial case. And when just V is equal to U, the same picture, but gap closes here, and when it's also greater than, band gap again opens. And the Jacques phase is quantized. So is topological phase transition. But there are so many number of hopping parameter here. It's Tx, Ty, U, and V. So it's better to understand. For the better understanding, we can just using one scheme, which is a decimation scheme, to map this ladder network in the SSH, which is the simplest model, simplest two-bond model, to understand this topological phase transition. Decimation means you are just rescaling it. You are just wearing a glass and you want to see just this size, not this size. But physics remains same. You are not decimating the wave the amplitudes, just rescaling it. And we are just decimated along this round. Now this all sides will be 2 by 2 matrices. Okay, and there is some change of basis. Okay, not going to the detailed mathematical calculation. Just look at here. This is the using the tide binding in the tide binding framework. This is the difference equation for this parent lattice. You can see here, and by decimating this, we are just recast it into a 2 SSH chain. One have the hopping is tx minus u1, alternating hopping tx minus u1 minus v. Another is same thing, just tx plus u and tx plus v. You can see here the same thing, or the difference equation from the SSH. Only just they are the rescaling. Okay. So from this equation, we can see that the band gaps will closes at this value. You can see here, this Ty is set to 4 and this 1, and epsilon is on-site potential, it is 0, it is set to 0, and you can see that band gap closes here. And by tuning this one by greater than this, following this trend, we can just opening up the gap at the Wilson boundary. So it is the easiest, it is one of the easiest way to solve the puzzle, which is a decimation scheme. Another interesting feature is to understand what is the position of this flat band. Flat band means it's a non-dispersive band. There is no kind of dispersion. This blue guy is the flat band here. If previously we have decimated from this parent lattice to this one, now we will rescaling it one more step and going into a periodic one, right? So this is the difference equation for this chain, and you can see this is the hopping parameter between two sides. If we set, just look into this one, if we set this tx minus u is equal to 0, then there will be no overlap between the wave functions of these sides. So electron will be trapped here. It can't move here and there. That's why there is no kind of dispersion. So we are getting a flat band, non-dispersive band. And the position of this band will be controlled by tuning these parameters. And it is doubly degenerate as we are taking u and v equal. What happens if we just unequal this u and v? The flat bands will be shifted. The degeneracy will be lifted up. Nothing else. For this flat band or non-dispersive band, there is a kind of amplitude distribution. What is this? This is called compact localized states. Means the amplitudes will be localized here in a compact way, so that it can't go from the electron when it looks into the system, it can't go from one side to another one. That's why there is no kind of dispersion. Here, just along the yellow shaded one, these amplitudes are non-zero, but here is 0, and again non-zero and again 0. Okay. Okay. Now we have already shown that we have the quantized surface from which we get from the bulk. That's why when we are just cut the system and put some open boundary condition, an edge state appear at the gap. Topological insulator means the surface states are conducting and the bulk is insulating. But it is for completely 1D case. That's why edge states are localized here. You can see for amplitude distribution for this gap edge state that the amplitudes are completely pinned at the edges of the system, and it is decaying when it is going to the penetrating to the bulk. Okay, that is the bulk boundary corresponds, and as the invariant is quantized, the phase is quantized, So the S states are topologically protected here. Okay, this one is another one is a three-arm ladder. Using the same prescription, we can describe this and recast it into a SSH chain. But the main interesting thing is that the central part will remain as a 1D chain, just like a 1D chain. Other upper and the lower part will give the flavor of the SSH chain. Hello?
Abhijit, terribly sorry to interrupt, but the 15 minutes are, so you might want to finish.
Okay. Yeah, sure. Thank you. Okay, so we will get the same flavor from this trium ladder network. You can see here there's a flat band which already explained in the previous case, and degeneracy is lifted, and this is band gap closes here, and again is opens up here, and there is a change of Jack phase, and the central part will remain the same. So just like a periodic 1D chain. And same thing from the this age state, it is completely pinched at the edges of the system, and it is decaying when it is penetrating through the bark. So there are many more experimental evidence. Just in warning, we have already learned about this for topological lattices in the field of photonics using the femtosecond laser pulse. We have already fabricated using this femtosecond laser pulse technique, and there's a topological A states, and also the topological flat band, because in case you can use this as a quantum information. Field of photonics. So, and they are my collaborators, Professor Arunabh Chakraborty from Presidency University, Srikanto Shil from Vishwabharati, and Atuni Nandi from APC College. And I am gratefully acknowledged Inspire for providing me the fellowship. So, thank you.
Thank you, Mukherjee, for the very nice talk. So it's now time for the question and answer session.
Okay.
So in the chat box, I see a question from Shobhi. He asked, in case of the two-arm ladder, we got two SSH chains after decimation. I couldn't get the three-arm ladder case. Can you elaborate it once?
Yeah, sure. Okay, for the three-arm ladder network, it is just you are doing this along this rung, you are just decimating this, and for this part, if you are just write down the difference equation for this central part, you will get the difference equation like this for simply periodic 1D chain. And for okay, this one will be better to understand. If we write down the potential matrix for this one, you can see after diagonalizing this one, you will get only these eigenvalues, epsilon minus root 2 ty plus and this epsilon. So for the central part, it is always like this periodic 1D chain. And for the upper and the down part, it will always get this to SSH chain. The same thing will happen when you are considering this five-arm ladder network. The central part will be like this, and the rest of four will be like this one.
I have a comment for Shovik actually. So just I want to
Yeah.
Shovik, uh,
Yes, sir.
the two-arm ladder is getting down to two SSH chains. It is not a result of decimation. It is a result of a change of basis
Chain
actually.
basis, right.
Okay.
Using the decoupling scheme, we are just change of basis.
Okay, I got it. Thank you.
Okay,
Uh,
I don't see any more. Okay, there is a
can I
question
ask
from
a
again.
question,
Yeah, yeah, sure.
Amrita?
Sir. Yeah,
Uh, this is due to the change of basis. So, what
right,
is the
right.
reason for this to recast the Hamiltonian in a convenient form? Are you changing the basis for that?
Yeah, that's why because you can see there are so many number of parameters. So that's the main flavor that we are trying to just decimate it is into SSH chain. That's the easiest way to tell about this phase transition by tuning what kind of parameter. That is the main flavor of this change of basis. Just we have to dealing with this 6 by 6 matrices, and now we are dealing just 2 by 2 matrices. That's the main thing.
Okay, thank you.
Just rescaling, yeah, rescaling the system.
Okay, thank you.
Okay, so I do not see any more questions from the participants. So let us thank Mukherjee for the very nice presentation. And now we will move to the
Thank
next
you.
presentation, which was actually delayed from the first presentation, and it will be delivered by Mohammad Tanvir Al. So, Shomadip, can you kindly share his slides because he was facing a problem? Okay, yeah, we can see the slides.
Hello.
Hello, yes, Mr. Alan, you're audible.
Hello. Audible, sir? Hello.
Mission, can you like raise the volume just a little? Your voice is coming very faint.
Hello.
No, yes, we can hear you.
Hello. All audible?
Yes, we do. We can hear you clearly.
Okay.
Shomadip, kindly share.
Okay.
Okay.
Thank
It's
you.
visible now. You
Thank
can
you.
start now, Mr. Alan.
Okay. Thank you for opportunity, giving opportunity. Sir, my topic is negative longitudinal magneto resistance in well semi-metal, and this topic is under the guidance of Dr. Devendra Prasad Singh, Associate Professor, BNN Mirpura. Sir, well semi-metals are topological states where the electronic bands disperse around the pair of nodes, well points, chirality left or right. The discovery of well semi-metals triggered exponential method for exotic quantum phenomena at chiral anomaly. From the chiral anomaly, non-orthogonal electric and magnetic field induced a chiral density imbalance for result of negative magnetic resistance. However, it is a question that what extent it survives when chirality is not defined. When the Fermi energy is far away from the well point, the Fermi surface forms spin polarized banana-shaped electron structure in the whole pockets attached to pair of well points. Although the chiral anomaly is not well defined, the observe a large negative magnitude magnetoresistance that appear in collinear magnetic and electric fields. Next, when we do experiment for well fermions semimeters, it has to identify that in which material well nodes are close to Fermi energy, by the quantum oscillation for the measurement of PAS and PAP, by the combination of band structure calculations, we determine the Fermi surface of those compounds. The distance of well nodes to Fermi energy is to 10 to 15 MeV in both compounds in clear. Fermi surface pockets separate surrounding each node in a pair of 12 nodes. 12 nodes. Well nodes where in each large pocket surrounds pairs. This is the result of well-defined generality and DFT. So, PJS compound is a choice of research in the chiral anomaly. The longitudinal magnetoresistance is very difficult to measure in clean compensated material due to their strong field induced conductivity and isotropy. Discussions and methods. Well fermions was first predicted in ferrochloride. This breakthrough comes in the beginning of 2015. After the prediction of well nodes in the band structure of compounds like PAS, DFE, NBS, NDP, this Fermi surface was confirmed by APRS, angle-resolved photoemission spectroscopy. These materials are well known and they are topological. After some time, there are a number of other materials proposed to well semi-metal. There are a number of other materials proposed to well fermion in bulk etc. can be obtained by chiral anomaly. In particle physics, there has been imbalance between the left hand and right hand fermion in the presence of parallel electric and magnetic field. Magnetic field. Well semi-metal, this will induce bulk negative longitudinal magnetoresistance. There is a strong report of the chiral anomaly in all four members of PJS family. The work about PJS family is a part is their search for experimental method of well fermions. There are theoretical prediction of well fermions in other physical quantities, but its chiral anomaly is very important. Introduction about fermion. The appearance of a Fermi arc is determined by the bulk band structure. Bulk band structure contains well points. The existence of Fermi arc of the well semi-metal is from surface states. Well semi-metal has a remarkable feature that for the unconventional surface states, which is known as Fermi arc, the discovery of the first well semi-metal in PDA provides the first observation of well fermion in nature, where we study about the topology of well semi-metal. We find anomalous surface state, Fermi arc, and well known. Uh, Fermions in nature find in the form of direct fermion, Majorana, and well fermion. Existence of new type of well fermion emerges at the boundary between the electron and hole. The appearance of well point is possible if the product of time reversal is not a symmetry of the structure. There is figure one left right point like surface Fermi surface and between the electron and hole pockets. Method used for finding Fermi arc of well fermion. First is by ARPS, angle-resolved photoemission spectroscopy. The shape of Fermi arc and their connectivity are shown first time in the TAS. Well semi-metal has a Fermi arc of its surface connecting projection of two well points with opposite chirality. From ARPS, Fermi surface map shows shapes Fermi arcs. By the ARPS, we can show map existence of Fermi arc without any theoretical calculations. By PPI found Kasi particle patterns, interface patterns. By the Kasi particles interface patterns, the state of the well semi-metals arises in PAS and thus can lead to theoretical calculations. These theoretical results are confirmed by experimental studies with clear evidence of well Fermi arcs in PAS using ARPS measurement. Keratian topology of the Fermi surface. We have to determine Fermi surface of TAP and TAS by using quantum oscillations. The oscillation is detected by detected resistivity as well as magnetization and magnetic torque for various directions of the magnetic field at low temperature. The sum of local density mean cells size of Fermi surface pockets and calculations alone are net uh, able to predict the shape of the Fermi surface. Experiments are needed to find the right method of calculation so that Fermi surface is produced. In TAP, Fermi surface consists of banana-shaped electron and hole pockets, and these pockets surround pair of well knots seen figure 1b and C. Banana shape pockets are longitudinal magnetoresistance of centimeter. All four members of TS family have been reported a negative longitudinal magnetoresistance by the study of Fermi surface of TAP. A magnetic resistance is not expected because the absence of correlating TAP. When magnetic field is parallel to the current, we find the voltage position influence strongly the measured magnetoresistance. This proves a field inhomogeneous current in the material. When a magnetic field perpendicular to the current in the direction of the conductivity in a compensated semi-metal strongly decrease with field due to orbital effect, whereas the conductivity parallel to the field remains constant. When the current enters the sample at a point like contact, it strongly straight in the direction to the field where the conductivity remains high and it forms a jet, hence when current jetting.
The speaker has left somehow, I think.
Hello? I think the speaker has left the meeting. I, I think we should wait for some time. I guess he's facing
We
some
should wait for
connection.
3 to 4, 5 minutes. We can mail him.
Maybe
I'm mailing.
bandwidth is or something. Let us wait for a few minutes. 3 or 4 minutes. Okay, it seems that the speaker is facing some serious connectivity issues and we are trying to contact with him, but we still cannot. So, please stay connected for 1 or 2 more minutes. We can see if we can contact him. Okay, it seems that we cannot contact the speaker, so unfortunately we will have to end the session now. We will ask him to upload his presentation in the Slack channel, so you can ask him any questions there in the Slack channel. So sorry for the unfortunate ending of the oral presentation session.
Yeah.
So
Okay.
in any case, so we will. Sorry. So in any case, so now we will have a break and we will start the afternoon session from 2:30 p.m. with the plenary talk from Dr. Sumanto Kundu. So with this, I end the oral presentation session here. So over to the host, Shovi.
Yeah, hello. I am really sorry on behalf of the ICCMSP team for this unfortunate ending of the oral presentation session. The talk was going on, and suddenly the speaker have maybe some internet issues also. So I would like to conclude the morning session here, and we shall resume at 2:30 p.m. We have a plenary talk by Dr. Sumanto Kundu from University of Padova, Italy, starting from 2:30 p.m. So please stay connected, stay tuned, everyone, and thank you all for listening. I would like to conclude now. Thank you.